All right, hello and welcome to Bite-Sized Biocompatibility episode 5, talking about sample preparation. In this episode, we'll be taking you through 10993-12, going through how you should prioritize the order of your testing from in vitro, analytical, then in vitro, before going into in vivos last. Yes. Talking a little bit about the ethics behind conducting animal testing, and also then touching on how -12 differs from -18.
Yeah. It's a whole bunch of valuable information for anyone looking at performing any biocompatibility tests. It's the first step in the process, we'll say, in executing these evaluations. And it's one of them that most people brush over too quickly and end up regretting it later. So it is definitely one of those things that will cost you a lot of time, money, and heartache if
you don't
overlooked.
do the due diligence there. Yeah, and it's definitely one of the most overlooked aspects within the industry, I think. So yeah, all right. I hope you enjoy. Hello and welcome to Bite-Sized Biocompatibility, the educational series focused on making the technical content of medical device biocompatibility digestible. My name is Leah Williams.
Hi, and I'm Beau Rollins with Intrinsic Medical Group, and we're excited to take you along on this journey.
All right. Hello and welcome back to Bite-Sized Biocompatibility, episode number 5. Today we're going to be talking about sample preparation and what you need to do before you start doing biocompatibility testing. So let's get right into it, I guess.
All right. I mean, when we talk about sample preparation, I guess the original question or the basic question most people have is, when do I use it and what do I use it for? So, I mean, you would use it for basically any of your in vitro or your in vivo assays, right? If you're going to conduct any of those evaluations. The one area that it doesn't really apply to, and where the exemption is going to be for -18, which is chemical characterization, which we talked about in an earlier episode. So don't get confused with -12 and thinking that it's applies to every test that you do.
Yeah.
It is the majority of them, and it has been around for quite some time, but it does not apply to chemical characterization.
Right. So I think going a little bit more off that, where does it apply piece there, you've kind of got, in biocompatibility testing, it kind of breaks down into that chemistry aspect, and then the, let's call it biological testing or the biocompatibility testing, which is more your in vitro and in vivo methods as well. So this -12 really is just for that biocompatibility testing portion.
Yeah, and it's I mean, there's definitely a hand in hand when it comes with -2. So -2 is going to be the animal welfare standard, and it's one of those that it brings in a lot of, and you see it in -1 with the 3 R's. So when you're going through with your sample preparation and sample determination for your testing, and that you want to take into consideration -2, which is animal welfare as well, ensuring that when you prep the test and your test articles and things that you're taking into account, any sort of adverse response or I will say incompatibilities that you may see with the in vivos. That's something that to really be cautious. Yes, you can have that with in vitros as well, right? Like there is incompatibility with possibilities with pretty much every test that we have.
Yeah, right.
But there's definitely a higher moral need around the animal welfare to ensure that, hey, if I'm going to be extracting a device that's generating particulates, that's going to be changing pH and osmolarity and things, that I'm taking that into account when I'm looking at performing an in vivo study, because you don't want to run into incompatibilities and suitabilities with the host just due from adverse reactions, from the extraction.
Yeah, that is such a good point as well. And I think that this actually is a really nice place to highlight how, when you're doing that, when you're setting up to do your biocompatibility testing, it really is so fundamental to make sure you've done that chemical characterization piece prior to that. And I'm not talking just necessarily about that data generation piece, that data gathering piece. Really understand your materials, really understand your device, and then a little bit more about maybe how that device would behave if you're extracting it, which is, let's face it, the primary way of preparing your samples for testing.
Yeah. Something that I think most people don't realize, and it's a valuable approach, is that you should conduct feasibilities if you're unsure. Like if you have a metal device or a hard polymeric device that you know isn't going to shed any particulates or change the chemistries of your extraction solution, then you don't really need to worry about this. But if you have anything that's degradable, soft polymeric and things, stuff that is going to cause your extraction solutions to be augmented from their initial forms, then you should look at doing a feasibility. Right?
Yeah, absolutely. I'm so glad that you mentioned that as well, because the thing is, the world of medical devices is so broad. You've got so many different types of medical devices, and then you've got not a finite number of different tests, but there's far fewer variations of different test methods than there are the number and variety of different medical devices. So it's not a one size fits all. You need to really understand your device and make sure how you can get that to work with the test method that you select for excuse me, evaluating an endpoint as well. So yeah.
No, I mean, and when we talk about feasibilities, the downside is -12 doesn't give you any direction on how to do a feasibility.
Yeah.
So it is something that is open to determination, right? And so some CROs are specific on how they want to do this, but not all of them will bring up the suggestion. So it is something that you, as someone conducting these tests as a biological evaluator, you want to make sure that you know your device, and if you know these types of issues, you propose it. Oftentimes I like to do the feasibility kind of extractions internally, right? Where I can play with hexane, cyclohexane, heptane, things like that.
Well, those would probably be more towards the chemistry.
That is more towards the chemistry. That is correct. That's a good catch.
But yeah, no, that it's really valuable if you do have even just an R&D laboratory that you have access to take your medical devices and just perform an extraction, just submerge them in whatever vehicle you're performing that extraction in, and just, even if you're just observing visually to see what happens, will it, significantly be compromised in terms of its structure if it's submerged for 72 hours at 50 degrees C in saline? What's going to happen? Take a bit of the extract, put it under a microscope. Do you have particulates? Just doing some of that basic characterization ahead of time really helps you down the line when you come to actually performing the test. And that links really nicely in with that replacement, reduction, refinement principle as well, with making sure that when we are going into animal testing, in vivo testing, that we're really using only the number of animals that we need to. We're not blindly going into a study, doing a full study and realizing that on day 2 there is some incompatibility, and you've got, just because of that material incompatibility, then you actually have to redo the whole test again with the same number of animals again, and that's a waste of life there.
Yeah. So. No. And when we talked about feasibility, I guess to wrap it up is how to conduct it. You want to replicate what you're going to do protocol wise. So same extraction times temperature solutions. You want to look at the same volume and administration route. You typically are just going to do it with one, and you can choose, like, if you see issues with polar and non-polar, but not with the non-polars, you don't have to do a feasibility with non-polar if you're comfortable there. So you would just be looking at like a one animal feasibility with the polar solution, right? And if you do see like particulates and other things and you're expecting challenges, then use the feasibility to potentially vet other options. So you would have your standard 50 degrees, 72 hours with, orbital shaking and saline, and we're going to have that as one variable for one animal. And then the other, maybe we try 37 degrees C, right? 72 hours or 24 hours. We augment those variables so that way it is in one swoop. We can potentially try to find the solution that's going to make that the official study, most plausible to succeed. And then you'll have that data to justify as well around your justifications on changing those parameters. Yeah,
100%. And I think both of us are kind of like maybe preaching to a choir a little bit here, but it's a topic that we're both super passionate about. And it's because we have this belief that setting up for the testing is probably the most under-considered part of biocompatibility testing. Everyone thinks that, 72 hours, 50 degrees C, you've got your non-polar and your polar solvents and jobs are good and off you go, it's going to work out. But why? I'm wondering if you can give us like a little bit more color on why actually we're in this position where we have these set parameters that everyone thinks, this is just how you have to do. how you have to extract a sample for.
It is a good question, one that comes up pretty much everyone who ever gets into biocompatibility is like, these are very interesting parameters and extraction ratios and variables. Why do we do them? And the scientists in us would love to say, oh, there's a reason why.
Here's the literature. Here's the study that says it.
And 37 degrees C, I think, is easy to explain, right? Because 37 degrees C is body temp, so that one makes sense. 50 degrees C, why? And what it boils back to, and this is something that predates even myself, as old as I am. What I've picked up from some of the experts prior to me was really that when this was getting developed, it was a reach out to all the different, because nothing was standardized at the time, so it was looking at what was being done. And so they looked across different universities and government labs and such, and grabbed a bunch of protocols from people and looking at what was being done for device type extractions. There was no guidance around it, and trying to find what looked like it worked, what was common between different labs, and that's really where the ratios kind of came in. They're not clinically derived, so that's something that a lot of people struggle with, and it makes sense. Like, I've had several regulators ask, you extracted at 6 centimeters squared per mil, how does that capture the device and the risk to the patient? And the reality is, I mean, clinically wise, it doesn't. It's just about being consistent.
It does capture that risk, but it is about that consistency piece. So, I mean, we do see if there is a risk in whatever study that we're doing, whether it's in vivo or in vitro. I'm putting an asterisk there because we'll talk about in later episodes as well that sometimes, you don't see everything, but it really is about having that consistency across the different test methods. So that's where I'd understood having that extraction ratio as well, like you mentioned. It's so we can actually compare the data between the results to some degree, even though you've got a variety of different methods that are available for use there.
I mean, the main point of Dash 12 was to allow for interlab comparisons, right? So if I run one at a lab and then 6 months later or a year later or someone else, or I need to run it again, I should be able to get comparable results because we're following the same aspects. But it's not derived around, thresholds of animal sensitivities. When we extract, we don't know what's in there. We've done it long enough and that to know that we do pick up things when there are bad things there. But as far as where they fall on that sensitivity, there's been quite a bit of work around genotoxicity and looking at these extractions for the in vivo models to find out that the sensitivity aspect is not that low, right? We're pretty, how I word that correctly, so that it's not that sensitive of an assay, maybe is the best way of saying it.
Right. And actually I'm kind of glad that you mentioned genotoxicity, because that is one of the ones where it doesn't immediately point you to Dash 12. It points you to Annex A, I think it is, in Dash 3, when it's got the method ABC in there as well. But we'll cover that in more detail later.
So it's a lot of this is about trying to think of worst case. That's why 50 degrees C is there. It was just a temperature. There's 70 degrees C, 120 degrees C.
And those are sort of more for accelerated extraction, I guess. So.
And I know there are a few people who have used like the 70, and there's probably somebody out there that used the 120. I would advise anyone to stay away from those.
It's just if you've got like a metallic implant, right? Polymers aren't going to like that.
Some agencies are going to definitely question that because it's not well vetted and things. You want to focus more around your 50 degrees C and your 37 degrees C. And if you're, you can look at with different times and evaluating your extractions, you can look at, amounts that's being, released over those time periods. So that way you can kind of create your extraction profiles and know just how much is coming off and when. You still don't know what's coming off, right? But in the end, if we look back at what a patient's going to actually see, no patient is going to submerge the device, entirely with mechanical shaking constantly for even 24 hours, right? Even an implant.
Very, very rare.
Yeah.
You're going to have a completely fluid solution that your device is going to be
circulating blood is going to be your most likely, if you had something put inside, circulating blood, at least you got flow there.
Yeah.
But you're still kind of, missing a lot of those mechanical forces that we do see. It's just keeping all that in mind, that the intent of Dash 12 is to be worst case. We are trying to pull out everything that we can reasonably get it to come out. But the key to you guys as people setting these up and evaluators is your integrity of your material and sample is the most important thing. So
Yeah.
balance that between what's clinically seen, and then making sure that your device is staying representative and not just breaking down or grading.
Well, that's actually a really good point there as well. I think in section 10 of the current -12, it does go into more details about kind of like what you need, or it might not be section 10 actually, but in -12, it does give criteria about what requirements there are for extraction, and one of those is that you can't have a significant amount of degradation of the sample. You can't see, what is it, significantly compromised, I believe that the actual wording is. But basically that means that if you're seeing your device behaving in a way that it wouldn't be seen clinically, or like way beyond that, then it's not representative of what's happening clinically. And I think one of the best examples we have here is if you have like super absorbing materials, for example, in a wound dressing. They're fantastic for function because they absorb vast quantities of exudate. But then if you're going to extractions, I've seen devices that absorb over a litre, more than that, and then they just keep absorbing until they literally completely fall to pieces, and all of that internal material that just wouldn't be present in clinical use kind of spills out of the device. It gets into the extract, and it makes the extract almost incompatible for testing as well. And you just wouldn't see that clinically.
No, well, I mean, if you absorbed a liter of solution from a patient, the patient's not going to be doing very well.
Right. And even if you were going to be getting to that point in clinical use, the clinician's going to take off the wound dressing and replace it with a fresh one before it explodes everywhere.
No, definitely. So there's a lot that factors into sample preparation. It's definitely a challenging area. It was kind of ironic because we talked about where do these come from as well, and I'm reminded that there was an initiative a few years ago to try and, I don't know if I'd say validate the method. It was more to verify the extraction methods with different materials. And I mean, in a nutshell, the study you can find if you want to search it up on -12. It's an open source publication, but it ended up being just overall kind of a disaster.
Disaster how?
There's a lot of materials that were selected to go through this and solvents and things. And as they went through, they found that a vast majority of them had to just be excluded from the study because it was incompatible for analysis, right? When they were trying to run these things through. And instead of, like as a manufacturer, we don't get the luxury of just saying, oh, it's incompatible for analysis, we can just move on. We have to, try to augment and everything else. But they didn't have that in the scope. They want to just standardize parameters. And when they were incompatible, they just omitted them basically. So it started with a pretty broad range of materials and temperatures and solvents and things, and it concluded with very few that actually made it through that they could analyze, and it just showed that this approach of -12 is not designed as a one-size-fits-all.
It sounds like the study that the industry needed to kind of demonstrate that actually you really do need to think about this a little bit more. You can't just go straight in with the let's call it the standard extraction ratios times temperatures and all of that.
So, I mean, one of the hopes of Working Group 12 going forward is that we can hopefully design and develop at least a validation, not to look at the solvents and the times. That already showed to be inconsistent, or not appropriate across all the materials.
Justifiable.
We want to focus on the extraction ratios. We want to look at, the 3 and the 6, 1, and really try to see what variances and differences we see with these across different materials. And yes, we'd ideally look at different temperatures and things like that, but really trying to see like where on these extraction ratios is there a difference? Is it critical or not critical? Do we need all those variations, or can we just more standardize it to one, or do we really need to have a variety? Because right now -12 has a lovely table, and the table's amazing.
Oh, we love a good table though.
Yes, we do. But most people just look at the top few rows of that table with the surface areas for thickness of material and then weight, and that's where they stop.
And there's sort of 5 or 6 different footnotes which kind of give exemptions from the table as well, and all of that.
And those footnotes can save your Well, I'll just say they'll save your butt. Yeah. When you're doing the extractions, because if you do have an absorbing or porous material or different things, like you get exemptions and augmentations down there that allow you to change it. And those will help you immensely a lot of times. So don't forget to look at the notes.
Yes. Look at the footnotes in table 1 in -12.
So, Leah, I'm going to ask you on this since you're the resident chemistry expert here.
Oh my goodness. I would like to apologize to all the chemists out there. I'm not a chemist.
Between the two of us, you are the resident expert in chemistry.
Good luck, people.
We mentioned at the very beginning that -18 is not part of, so chemical characterization is not really part of -12. So what is the difference between these two then? If it doesn't apply, what do we expect to see the difference?
Yeah, so I mean, there's a number of differences between the two standards, but I'd say that for me, the major one is actually in how you conduct that extraction. And for me, it is that ratio portion as well, because in -18, when you're doing an evaluation, you're trying to look at the per device exposure. And actually, I'm kind of glad that you threw that question to give me that segue into that, because I wanted to bring that up. And that's honestly, I'd like to see -12 adopt more of that, because I know that we want consistent extraction ratios to be able to compare between labs, compare between different test methods, and have an idea of the dosing. But if we still had that per device, you'd still be able to compare the different test results for each device as well. So yeah, I'd really like to see -12 adopt kind of like that per device extraction principle from -18. And then, because all of the different, especially in vivo methods as well, you've got the different doses that you have for the different animal models. So you're already scaling it in that way. And to me, if you're using the -12 extraction ratios, well, if you're already going to scale it to a different dosing, then what's the point of using it? So I know I kind of went a bit on a tangent. I wanted to talk about that instead.
That's a very good point that we'll get to when we get into systemic toxicity, and that is around dosing volumes and the variability there. And you're right, having different extractions into that, and how does that play?
And then I guess the main other difference that you see between -12 and -18 is actually those extraction vehicles, the solvents that you use to perform any extracts as well. And usually the ones that you use for the chemical analysis, they were very much targeted to be compatible with the different analytical instrumentation, and those are very much not compatible with with animal models.
As Leah caught on my earlier one, do not use hexane or cyclohexane or heptane or any of those to extract ethanol for in vivo studies, please. That would be disastrous consequences. So out of clarity then, if those are definitely -18, what are extraction options or typical solvents that we see with -12?
Yeah, so you have your polar ones. So usually you'd go with saline for that. It's compatible if you're doing any injection studies, for example, with the animal. And then you'd have your non-polar. So that will be typically an oil-based, and we see things like sesame oil, cottonseed oil. Most vegetable oils, actually, I think are okay for use there as well.
I've occasionally seen an olive oil and even an avocado, I believe once I saw someone propose using an avocado oil.
That's exotic.
I know. I think some labs like to get creative and try different things. Does it work? In theory, yes, it's allowed, and you can go through and you want to verify that. I would always caution anyone executing, just be aware that if you do use olive oil or avocado oil,
something a little more tropical,
you may get questions, right? And so you want to make sure that you've got some sort of supporting data around that oil and why it's okay. I mean, you have a control that you're gonna be running with it anyway, so that might be necessarily all that you need. But industry, as you said, standard is definitely going to be like cottonseed oil and sesame seed oil. Those we see all the time.
100%. And then just to wrap things up on this episode, I think we kind of just jumped straight into the testing and sort of threw around that we use animal testing. I think actually it would be a good point to take a step back here for anybody who maybe wasn't aware that it's probably the dirty secret of medical devices is that we do still perform animal testing. And it's unfortunately, there are just some in vivo models where you get that data that you just can't get to capture the risk of some devices with any other models yet. And as an industry, there's a lot of activity trying to move away from in vivo models, going to in vitro alternatives, or you hear the term NAMs, or non-animal models, or new approach methodologies. There's a couple of definitions out there thrown around quite a lot. And yeah, it's an unfortunate reality of where we are, in 2026, still doing animal testing.
I'm glad you pointed out. I mean, definitely, I would say there's a strong initiative from several members in the community to drive, more non-animal methods. And so there are new in vitro methods. I call them new because they're new to medical device. They're not new to industry. They've been around for quite some time. They're accepted in all other markets and that, right? So cosmetic, pharma, and things. And the people ask me oftentimes, like, why are we
still doing animal testing when pharma, cosmetic has moved away from it?
Yeah, and it really, just as a side note, I know this might step a little bit away from -12, but it's really the concern and the risk is around extractions. When you're extracting from multi-component and material devices and you're creating this soup mixture of weak compounds, strong compounds, and ones that can have synergistic aspects, the continual worry and risk is that are these in vitro methods able to detect these things accurately and appropriately, especially around those weak compounds. Like if it's a weak irritant, how do we know that this method, this assay is going to pick it up?
Yeah, I mean, I'm going to play devil's advocate there a little bit, and that typically having an isolated tissue or cells, typically from my experiences, are much more sensitive than a whole animal model. But it's about having those synergistic effects within your messy medical device soup, let's call it, extract.
I think at the end, what we fail to accurately ask ourselves is we're already accepting an animal model as being accurate and able to detect these weak things.
Yeah.
And there's no way to really be able to do that when we do, comparisons. There are differences between in vivo and in vitros, but anytime someone's followed through with human, usually the in vitro and the humans align, and it's the animals that's out because they mispredict for humans. We're not the same.
And in human model, in vitro models, you can actually use human tissues and human cell lines as well. We don't use them for every single one just because of how the models have been verified or validated. Again, as we'll touch on in future episodes, but yeah.
So as we get into the different endpoints, and I still call them endpoints, even though now they're not considered endpoints anymore.
With the 2025 update, it's now effects.
Yes. We're now dealing with harms and that. But, as we talk about these risks to evaluate through the future episodes, we'll discuss the in vitros, the in vivos, that are applicable and appropriate in each one of those. So we just wanted to touch base on it, I guess, here with the -12, and keep in mind that, yes, we always want to target, and that's what -2 and 12 push along with -1 is that you start with analytical chemistry, then in vitros, and then in vivos. That's the order of approach that should be taken. And then for anyone new to this industry, just also please be aware that every country and regulator approaches this differently. So you want to make sure that you are aligning your testing strategy for the markets and regions that you're submitting to.
That is such a fantastic point, and I feel like we could spend so much more time discussing that. But yeah, we are coming towards the end of the time available for this episode. But
I was going to say I can keep talking about like manipulations of device extracts and things that we can do. There's a vast discussions and things around sample extracts. But yeah, I think
we're in the name of keeping it bite-sized. Then we'll come back to it in season 2.
Maybe.
So all right. So yeah, I guess we're closing it out now. Well, thank you very much for joining us for another episode of Bite-Sized Biocompatibility. Whilst you're digesting this information, feel free to reach out to myself or Beau on LinkedIn. And we look forward to hearing from you and seeing you in the next episode.